I am Sunanda. I am super excited to welcome you to this learning session brought to you by Gudsky Research Foundation. Our foundation is committed to helping students and learners from all backgrounds gaining knowledge in cutting edge technologies like artificial intelligence and machine learning. It's free of cost. We believe learning should be accessible to everyone, no matter where you are or what resources you have. That's why we are offering a 6-month educational series designed to guide you step by step through basics of AI and ML, starting from scratch. Today's session is all about statistics and probability for machine learning. Whether you are just starting out or already familiar with such concepts, this session will explain everything clearly with definitions, real world examples, and scenarios you encounter every day. So sit back, relax, and let's learn together. This is your space to grow, experiment, and explore. So now we'll move first slide. Why statistics and probability in machine learning? Okay, now you might be wondering, why do we even need statistics and probability in machine learning? Well, let's start from the basics. Machine learning is all about teaching computers like how to make sense of data and make decisions. But data is wherever, everywhere, like it's incomplete or it's uncertain. That's where statistics and probability come in. Statistics helps us summarize large amounts of information. For example, imagine you run an online store and want to know how products are performing. Instead of going through thousands of orders manually, you can calculate the average order value or spot trends in customer behavior. Probability helps us deal with uncertainty. Real world data isn't always perfect. Sometimes values are missing or outcomes are random. Probability helps the system account for this randomness, like predicting the weather based on past patterns or guessing what movie you might enjoy next. It also helps us check how accurate our model is. For instance, after training a model to recommend books, we want to measure how often it gets it right or wrong. So in short, statistics and probability helps us understanding data better, like helps analyze and summarize data with measures like average, spread, and patterns. And it also deals with uncertainty like missing values, unpredictable or misbehavior of the data. Like, and also after this it will make predictions, like helps algorithms forecast and outcomes and classify new data. And from the past data it will may predict, and also it will check the accuracy measures, like how model performs and where it can be improved. And it also used in everywhere, like healthcare to finance, recommendation to automation systems. And apply these skills in field like healthcare and more. Without these tools, machine learning wouldn't be as powerful or accurate. Okay, now we'll move for next slide. Roles of statistics in data analysis and modeling. Let's now talk about how statistics play a major role in data analysis and modeling. Suppose you are working on a dataset for predicting student performance. You have data like study hours, attendance, and previous grades. What can you do with it? First, you explore the data. This means you look at patterns like how attendance is related to grades. Are students with higher attendance scoring better? This process is called data exploration. Next, you try to identify patterns and relationships. Maybe students who study more than 5 hours perform better, or students in certain regions perform differently. These patterns guide how you build your model. And the next step is feature selection and engineering. You choose which pieces of information, and it means features, the most useful. For example, study hours might be highly predictive of scores while favorite color might not add much value. You can even create new features by combining existing ones, like study hours per week. Then you evaluate your model's performance using matrices like accuracy or error rates. For example, how often does the model correctly predict whether a student will pass or fail. Finally, you use the results to make informed decisions, maybe recommended extra classes for students who show a lower probability of passing or suggest changes in the curriculum. So, this is where statistics helps you start to finish understanding modeling and making smart decisions. Right? This is the way I'll explain here. Now, we'll move for real world applications in ML. Machine learning isn't just theory, it's something that touches almost every part of our lives. Let's look at some real world examples. Let we go for a healthcare example. Machine learning models help predicting diseases like diabetes based on patient data. They can also personalize treatments, for instance, recommended diet changes to manage blood sugar levels. And we'll go for finance. Finance in ML predict and detect fraudulent transactions in your bank account. It looks for unusual patterns like a sudden spike in spending and alerts you immediately. It forecasts stock market trends to help investors to make decisions. And if we go for retail and e-commerce, have you ever wondered how Amazon or Netflix recommended products or movies? It's based on your behavior, what you searched for, clicked on, or purchased before. Machine learning helps find similar patterns among users to recommend items you will enjoy likely. And transportation, as we everybody knows now, self-driving cars rely on machine learning to make real-time decisions. This system constantly processes information from cameras and sensors to avoid accidents and choose the best route. And if we go for social media like Facebook or Instagram filter content and it detects spam and recommend posts you'd like based on interaction patterns. These examples show how statistics and probability don't just stay in classrooms, they power tools that solve real problems and improve our day-to-day lives. Okay, now descriptive statistics. Now that we understand the applications, now we'll move to descriptive statistics. So, what is descriptive statistics? It is the process of summarizing and describing data in a way that's easy to understand. Imagine you have a dataset with thousands of entries, like customer reviews or transaction record. Without summarizing it, you would be lost. It is the way descriptive statistics helps by showing patterns, trends, and important features that make sense at a glance. Let's look at some common tools like mean, median, mode, range, and variance. So let we simply see what it means. Mean means average. This is the sum of all values divided by the count. For example, if the ratings of 5 products are 3, 4, 5, 4, 5, then the mean will calculate the will sum of the all products and then divided by the 5. 4.2 it means we'll get the value. This helps you quickly know how customer generally feel. Median means the middle value when the numbers are sorted. If the sorted ratings 3, 4, 4, 5, 5, the median is 4 here. It's useful when you have outliers like one very high or very low rating. Mode. This is the value that appears more often. In the same examples, ratings 4 and 5 appear twice, but if one value appears more frequently than the mode, it helps identify the common data points. Range and variance means the range shows how spread out the data is by subtracting the smallest from the largest value. Variance tells how much each value deviates from the mean, showing us the consistency and inconsistency in the data. In machine learning, descriptive statistics is essential because It helps us prepare and interpret the data before we feed into algorithms. Hope you understand. And the next slide is types of data. Types of data. Understanding the types of data is key before applying any statistical methods. Here, data can be classified into different types based on how it's structured and what information it holds. Like if we go for categorical data, this is the data that fits into groups or categories without any specific order. For example, car brands like Toyota, Ford and Honda, you can group data but can't say one category is better than the other, because every it's have own their features. And if we go for numerical data, these are numbers that can be measured or counted. For example, age, height, weight. This data is useful in performing calculations and statistical analysis. You can add, subtract or calculate averages here. And the original data means this is the data where the order matters, but the difference between values isn't always equal. For example, education levels like primary school, high school and college, these are ranked but don't have consistent intervals between them. Knowing the type of data helps us choose the right statistical tools. If you treat ordinal data like numerical data without checking the nature, you might get wrong results. So classification isn't just a formality, it's the foundation of proper analysis. And now we'll go for measures of central tendency. How to find the central point in a dataset. This helps to understand the overall trend of data easily. There are three major measures, as we previously discussed about it, like mean, median, mode. The mean is the average of all values. Example, for the numbers 5, 10, 15, here they summed all the 5, 10, 15 and there are 3 numbers, so divided by 3 we get the value 10. Median means the median is the middle value where the data is arranged in order. For example, the numbers 3, 7, 9, median equal to 7, so it is the middle number. For 3, 7, 9, 11, we will calculate this like median. 7 plus 9 by 2 equal to 8, so the median number equal to 8. The mode is the value that appears most frequently in the dataset, like more numbers. For example, the numbers we take here 2, 4, 4, 6, 8. Here the frequently came 4 because it appears more than once. These measures helps us summarize data easily and make better decisions when building machine learning models. And whether analyzing sales, test scores or website traffic, understanding these helps you to get a quick summary of the data set. And now measures of spread. While central tendency tells about the average, measures of spread tell how data is scattered around the mean. Spread is important because it helps us understand variability. Here in spread there are range, variance and standard. In previous we discussed about mean, median and mode. Okay, now we'll see range. This is the simplest measure. It's the difference between the largest and smallest value. For example, the numbers 4, 8, 10, 15. Range equal to 15 minus 4. So the difference is 11. So this is the range of the given numbers. And the variance. Variance shows how far each value is from the mean on average. It gives an idea of how spread out of the data is. As we take an example for the numbers 2, 4, 6. So mean means the average of all three numbers equal to 4, and the variance is about like calculating like each number minus with 4, which means mean, and doing the square, and for all the numbers we'll do like that. Then we'll divide it by 3 because they're given 3 numbers. So equal to 2.67. And standard deviation. Standard deviation is the square root of the variance. It is easier to interpret and shows how much the data deviates from the average. Okay. Example, here we take 2, 4, 6. The standard deviation is 2.67 and approximate value is 1.63. Okay. These tools are used in risk management, quality control, and almost every data driven choose decision making process. Now, quartile and in-quartile range. Sometimes we want to look at data is distributed rather than just its central value. That's where quartiles and in-quartile range come in. Quartiles divided into 4 equal parts, like 4 in a square, 4 parts. Imagine like that. In first quartile, the value below which is 25% data false, and the second quartile is the divides the data set in half. In the value below which 75% of data falls. The in-quartile range is the difference between Q3 and Q1. It measures the spread of the middle 50% of data, helping to understand how concentrated to the data set is. For example, if we take the score 3, 5, 7, 8, 12, 15, 18, Q1 equal to 5, Q2 equal to 8, and Q3 equal to 15. So, in quartile range here is 15 minus 5. That means 10. So, this helps detect outliers, values that are unusually high or low. For example, in salary data, a very high earner may skew the average, but the IQR means in quartile range gives a clearer picture of typical salaries. Okay, here I used the word skew. Next we will see in the next slide what skew means. So, skewness and kurtosis. Finally, let's explore how the shape of data looks using skewness and kurtosis. Skewness tells us whether data is balanced or titled. If most of the data is small with a few larger outliers, outlier means the rare part and not recent one, like odd one out, the distribution is positively skewed. If most of the data is large with a few smaller outliers, it negatively skewed. For example, if you track the income levels in a city, the most people earn low wages, but few are extremely wealthy. You will see here a positive skew. Kurtosis shows whether the data disruption is sharp or flat. High kurtosis means there are more outliers. Sudden jumps in stock prices or rare weather events. This is positive. And low kurtosis means the data is smoother with few extreme values. A normal distribution like heights of people usually has a moderate kurtosis, forming the familiar bell-shaped curve. Understanding skewness and kurtosis helps analysts decide how to approach data modeling and whether any judgments or adjustments are needed before applying machine learning algorithms. And now we'll move to the next topic, like visualizing data histograms and bar plots. Here histograms mean shows the data, how data is distributed across ranges, like 60 to 70. Like I'll explain the diagram first. Taller bars means more values in the range. For example, test scores grouped in ranges like 60 to 70, 70 to 80. So these are the ranges, and the taller bar are mean more values, and box plots. So it shows the smallest, largest, middle values and where most data lies. Okay, and it will highlight the outlier part. That means outlier means odd one out, like which is not same as the others. Example, monthly expenses showing typical range and extremes. Now this is all about visualizing data. Histograms are box plots. It is for visualizing the data. All we previously discussed about it. And now what is probability? Now let's dive into probability, one of the most important concept in machine learning. Now probability is a measure that tells how likely an event to occur. It's expressed as a value between 0 and 1. 0 means the event is impossible. 1 means the event is certain. Okay, anything between 0 and 1 shows how likely or unlikely something is. Okay, let me give you an example. Tossing a coin that has two possible outcomes, head or tails. So the probability of getting head is 0.5 and tail is 0.5. So equal chances. And rolling, and we'll go for next example. Rolling a 6-sided dice has 6 possible outcomes. So the probability of getting a 4 is 1 out of 6, right? Which is approximately value of 0.167. Probability also plays a role in everyday life. Like what's the chance it will rain tomorrow? Like how likely are you win a lottery ticket? In machine learning, probability helps us make informed guesses where the data is uncertain. For example, when a spam experiment, sample space and events. In probability there are three important terms to understand: experiment, sample space and event. Experiment is, this is an any action process that leads to outcomes. For example, tossing a coin, rolling a dice or drawing a card. So here sample space is the set of all possible outcomes of an experiment. So if we toss a coin, there are two options like head and tail, and also if it dice make a roll, there are 6 possible outcomes. There are sample space 1 to 6. Okay, here event means this is a specific outcome or group of outcomes. Example, in rolling a dice, the event getting an even number 2, 4, 6, and tossing a coin getting head. Okay, this is the event that likely occurs. So the probability of an event calculated by dividing the number of favorable outcomes by the total number of possible outcomes. So the probability is directly tied to how you define your sample space and event. Now we'll move to next slide. Classical versus empirical probability. There are two main ways to calculate probability. One is classical and one is empirical. This is based on theoretical reasoning, assuming that all outcomes are equally likely. If we take an example here, a fair dice have 6 sides. The probability of rolling a die and getting 4 is 1 by 6, because there is one favorable outcomes and 6 total outcomes. Okay, and we'll go for empirical data or empirical probability. This is based on observed results from real world experiments rather than theory. Example, if you toss a coin 100 times and it lands heads 55 times, the probability of head is estimated as 55 by 100. It means 0.55. This is practical because in real life outcomes may not be perfectly random. Machines may have biases or other factors influencing results. And key takeaway, classical probability is theoretical, empirical probability is based on actual experiments and observation in real world. Machine learning models use both types to predict real world events, especially when historical data is available. And now we'll see the probability rules. Once you understand basic probability, it's important to learn how to combine events. That's where probability rules come in. Addition rule. Addition rule means it helps you when you want to know the probability of one event or another event happening. So here we given a formula like P of A or B equals to P of A plus P of B minus P of A and B. If we take an example here, rolling a dice, what's the chance of getting 2 or an even number? Here P of 2 equal to 1 by 6 chance. Okay. P of even equal to, even means in a dice we'll have even numbers 2, 4, 6, right? And 3 by 6. It means P of even equal to 3 by 6 and P of 2 and even 1 by 6. So P of 2 are even equal to 1 by 6 plus 3 by 6 minus 1 by 6, that equal to 3 by 6. The subtraction prevents double counting, right? And multiplication rule, which means intersection. It helps when you want to know the probability of two events happening together. Independent events, that means the outcome of one doesn't affect the other. Example, tossing two coins, that means P of heads and example, if we take two coins of tossing, that leads to P of head and heads, that equal to 0.5 and 0.5 chances, that equal to 0.25. Okay. And dependent events means the outcome one affects the other. Example, drawing two cards from a deck without replacement, like P of as and another as equal to 4 by 52 and 3 by 51. Okay. These rules help solve complex problems like calculating probabilities in games, experiments and predictive models. And now we'll go for independent and dependent events. Understanding whether two events are independent or dependent is crucial because it determines like which formula to use when calculating their combined probability. Independent event means the result of one event has no effect on the result of the other. Example, tossing a coin and rolling a dice. What you get on the coin doesn't influence the dice of roll. Okay. Dependent event means the result of one event influences the result of the next event. Example, drawing two cards from deck without replacing the first one. After removing one card, the total number of cards decreases, which affects the chances of the second draw. Knowing this helps us choose the right approach, and when working with probabilities, it's a small but important step in making accurate predictions. And now, conditional probability. Conditional probability is a powerful concept that helps us adjust our understanding based on new information. It's the probability of an event happening given that another event has already occurred. Here we'll see the formula P of A by B equal to P of A and B by P of B. Okay. P of A mod B is the probability of A given B has occurred. P of A and B is the probability both events happen. P of B is the probability of that event B happens. Let's say you are drawing a card from a deck. Event A is drawing an ace and event B is drawing a red card. There are two red aces out of 26 cards. So P of A B equal to 2 by 26 equal to 1 by 13. This approach is widely used in machine learning, for example, updating spam detection based on new patterns or refining predictions as more data becomes available. Okay. Then we'll go for Bayes theorem. Bayes theorem helps us revise our probability estimates when new information comes in. It's extremely useful in areas like medical diagnosis or fraud detection. We'll see Bayes theorem definition. It's a mathematical formula that updates the probability of an event based on new evidence. Like if we see the formula here, P of B by A P of A by B equal to P of B by A into P of A by B by P of B, where P of A is the prior probability or what you believed before seeing new data. P of B by A is likelihood or how likely the new data is if A is true. P of B is the total probability of seeing B. P of A by B is the updated or posterior probability after considering the new evidence. Okay, if you won't understand, no problem. Let me see a quick example for your understanding. Here we take medical diagnosis. It's medical test. Suppose the chance of having a rare disease is 1%. Imagine like that. A test identifies the disease 99% of the time when it's present, but also incorrectly flags healthy people 5% of the time. Bayes theorem helps you calculate how likely it's really is that you have the disease after testing positive. This is the theorem is widely used in AI systems to make smarter decisions, especially when dealing with incomplete or certain information. Now we'll see random variables, discrete versus continuous. In machine learning, randomness is everywhere. That's why understanding random variables is important. Let me see a definition. A random variable is very important in machine learning. That is the value that depends on the outcome of a random process or experiment. It represents like uncertainty or variation in the data. There are two types: discrete random variables and continuous random variables. These take specific count and countable values. Example, number of heads in 3 coin tosses. Possible values are 0, 1, 2 or 3. Continuous random variables. These can take any value within a range and are often measured with decimals. Example, temperature measured in a city. It could be 25 like if we see 30.5 degrees Celsius, 30.55 degrees Celsius, etc. Both types of random variables are used in models to represent features like age, income, test scores, or even sensor data in devices like self-driving cars. Many models use random variables to represent features or predictions. So, this is helpful to give more predictions for future. And probability distribution functions. Once you know the type of random variable you are dealing with, the next step is to understand how its probabilities are distributed. This is where probability distribution functions come in. If we go for definition, probability distribution function, it describes like how probabilities are spread over different outcomes of a random variable. These are two types: possible probabilities mass function, which is also known as PMF, and probability density function. So PMF used discrete variables. It shows the probability that a specific outcome occurs. Like rolling a dice, here P of x equal to 3 equal to 1 by 6. That means getting a chance of, if we roll a die, there will be a 1 chance of getting one number, right? So this is the probability mass function. And probability density function means used for continuous variables. It shows how likely values fall within a certain range. Example, heights. Heights means the probability of someone's height is between 160 centimeters to 170 centimeters. Understanding how values are spread helps machine learning models make better predictions by understanding or identifying patterns and trends. Now, Bernoulli and binomial distribution. Let's now look at distributions that are widely used in machine learning. Bernoulli distribution means it's used for experiments with only two possible outcomes, success or failure. In every chance or in every day-to-day life, there are two things, right? If we do a thing, it will be success or failure, no other thing, right? So this is what Bernoulli distribution. Example, tossing a coin, head equal to success, tail equal to failure. Okay, the mean of Bernoulli distribution is just p. P means the probability of success and the variance is p of 1 minus p. Okay, this is Bernoulli distribution. And binomial distribution means this describes like how many successes occur in multiple independent Bernoulli trials. Trials means many times. Example, how many times head appears if you toss a coin 10 times. Okay, the mean is n into p, where n is the number of trials and p is the probability of success. The variance is n into p into 1 minus p. Nothing just here. Bernoulli distribution means p into no. Bernoulli distribution means just p, and the variance, that means the event not gonna be success, that is p of 1 minus p. That's all. So binomial distribution means the event that is going to success, here n into p, and the event that is not going to success, which means failure, n into p into 1 minus p. This is the Bernoulli and binomial distribution. These distributions are fundamental in solving classification problems, simulations, and understanding repeated processes in AI and ML applications. Now, Poisson distribution and normal distribution. Now, let's see two important probability distributions that are widely used in machine learning. One is Poisson distribution and normal distribution. Poisson distribution means the distribution that is used model rare events, things that don't happen very often but are still important. So, if we take an example here, imagine a customer service center where complaints are rare. The Poisson distribution can help predict how many complaints you might get in a day. It's defined by the parameter lambda, which is the average number of events expected in a fixed period or space. If we see an example here, number of customers complaint per day. If the customer service team receives an average of 5 complaints per day, lambda equal to 5. You can calculate the probability of receiving exactly k complaints using a specific formula here. And now normal distribution means it also known as Gaussian distribution. This is the one of the most common distributions in the world. It's symmetrical and forms the famous bell-shaped curve. It's used when data is spread evenly around the average value, like people's height or test scores some interesting properties. The mean, median and mode are the same. About 68% of data falls within one standard deviation from the mean. About 95% falls within 2 standard deviations and 99.7% within 3. Example, in a class of 100 students, the most scores will be around the average with only few scoring very low or very high. These distributions are essential for probabilistic modeling, understanding data patterns and making predictions in machine learning. And now we'll move for Z-score and standardization. Once we understand how data is spread, we need a way to compare the different data points and normalize them. That's where Z-score and standardization comes in. Here let me see definition first. A Z-score tells how many standard deviations a particular value is away from the mean. The formula is Z equal to x minus mu by sigma. X is the actual value and mu is the mean of the dataset and sigma is the standard deviation. Let's say the class average is 75 and the standard deviation is 5. If a student scores 85, the score is 85 minus 75 by 5, that equal to 2. This means the student scored 2 standard deviation above the mean. Why it is useful means it helps compare the data from different distributions. It's widely used in machine learning models that requires features to be scaled. It helps in identifying outliers, data points that are significantly different from others. Standardization or scaling data makes algorithm perform better and ensures fair comparisons between variables. Hope you understand Z-score standardization, and next we'll move for what is inferential statistics. So far we have been dealing with data directly available to us, but often we can't collect data from every person or object, right? This is where inferential statistics come into play. So we'll see the definition here. Inferential statistics involves making predictions or drawing conclusions about a larger group of population based on a similar sample of data. Example, a survey of 500 students can help predict the average exam score of all 1000 students in the school. Even though you don't have data from every student, you can still make reliable conclusions. So key concepts of inferential statistics is estimation, hypothesis testing and confidence intervals. Estimation means guessing population parameters like the average score, and hypothesis testing means checking whether a new method is really better than the existing one, and confidence intervals means giving a range where the true value likely lies. This is a powerful in machine learning because it helps models generalize from small amounts of data to make predictions about larger explanations. Okay, and sampling and sampling distribution. So what is this? So sampling is an important step when working with large dataset. Instead of analyzing all the data, we take a smaller part, a sample, and use it to learn about the entire population. Sampling means choosing a subset of data from the larger population. Sampling distribution means this shows how a particular statistic like the mean behaves across different samples from the same population. There are different sampling methods. Random sampling means every individual have an equal chance of being selected, and stratified sampling means the population is divided into groups and samples are chosen from each group. Systematic sampling means every nth individual is selected, and cluster sampling means the population is divided into clusters and a few clusters are randomly chosen. And if a company wants to know customer satisfaction, it doesn't need to survey all 10,000 users. It can randomly select 1000 users and estimate the overall satisfaction score. In machine learning, sampling helps in training models efficiently, the avoiding biases in data collection. Now LLN, which means law of large numbers. Now let's look how a sample size impacts the accuracy of our predictions with the law of large numbers. The law of large numbers states that a sample size increases, the sample mean approaches the true population mean. Example, if you toss a coin only 10 times, you might get head 7 times and tail 3 times, which is not close to the expected 50-50 distribution. But if you toss it 1000 times, you will likely get a closer to 500 heads and 500 tails. Okay? And classroom scores. Sample 5 students mean score may vary widely. Sample 500 students mean converges to the true class average, right? So this is what law of large numbers. Bigger data sets give more accurate predictions. It's especially useful in machine learning where algorithms learn from sample data. It ensures that model generalize better by reflecting true patterns rather than random noise. So the larger the sample, the more confidence we can have in our predictions. Okay. Now we'll move for hypothesis testing. That means sometimes we need to check if a new approach is ideally and actually it's better or not. That's where hypothesis testing comes in. So there are two types, null hypothesis and alternative hypothesis. Null hypothesis means assumes that there is no effect or difference, and alternative hypothesis means assumes that there is an effect or difference. Okay, let's say a new teaching method is introduced. H0 means the new method has no impact on student performance, and the H1 is the new method that improves student performance. The process involves formulating H0 and H1 and collecting the sample data, calculate the results and compare them, accepting or rejecting H0 based on the significance level. Here, drug effectiveness. Example we take, drug effectiveness is H0, that means no effect. H1 is improves recovery. In ML algorithm, H0 means new model performs same as baseline, and H1 means new model that performs better than previous method we are using. In machine learning, hypothesis testing helps determine if improvements in algorithms are due to better methods or just random variations. Now, p-values and significance levels. Once we set up hypothesis testing, we need tools to decide whether our findings are reliable or due to chance. That's where p-values and significance levels comes in. Definition means p-value means probability of obtaining results as extreme as the ones observed, assuming the null hypothesis true. Okay, significant level means this will be denoted as sigma, and the threshold below which we reject the null hypothesis, a common value is 0.05, meaning 5% chance that the results are due to random variation. If we go for example, A by B testing is a common scenario where you check a new website design improves click rate. If the p-value is less than or equal to 0.05, you can confidently say the new design is better. A smaller p-value means stronger evidence against the null hypothesis. In machine learning, this ensures that features or models are genuinely contributing to improved predictions rather than random noise. This is all about p-values and significance levels. And now, bias versus variance trade-off. Now let's talk about one of the most critical concepts in machine learning, the bias variance trade-off. So in ML, these are the common terms we used in bias and variance. Error, that means bias means error. Error that occurs when a model oversimplifies the relationship between inputs and outputs. It leads to underfitting, means the model can't capture the true patterns. Okay, and variance means the error that comes when a model is too sensitive to training data, capture noise rather than patterns. It leads to overfitting. when the model doesn't generalize well. Example, you are training a model to predict house prices. A high bias model might ignore important factors like location, resulting in accurate predictions, and a high variance model might fit every single detail in training data, performing poorly on new houses. So this is what bias and variance. Now we'll move for bias variance trade-off. The process of balancing of bias and variance to minimize total prediction error. Total prediction error means bias square plus variance plus irreducible error. We aim to find the right balance between simplicity and complexity to minimize total error. This balance helps ensure models learn effectively without memorizing irrelevant details. So this is what bias and variance trade-off. And in ML relevance guides model selection, hyperparameter tuning and generalization to new data, and experimental results preventing misleading conclusions. So this is the bias variance trade-off. And now we'll move for underfitting and overfitting. So as we previously discussed about bias and variance, this is closely related to bias and variance or underfitting and overfitting. So underfitting means this happens when the model is too simple and capture patterns in the data. It ignores the main key features and poorly perform on both training and test data. Example, if you use one feature like number of rooms to predict house prices, you may miss out another critical factors like location or amenities. And the overfitting means this helps when the model is too complex and fits the training data perfectly but fails to generalize the new data. Example, a model that memorizes every past data point rather than learning patterns might work well on training but fail when predicting prices for new houses. Okay, and the goal is to build models that generalize well to unseen data by finding the right balance. Okay, this is what underfitting and overfitting. As we see many things like differences here, model is too simple to capture patterns in the data, and here the model is too complex and captures both patterns and noise in the data. And the definition will go for definition. It is high error and this is low error, and training error is high and here high and poor generalization, and test error means high, here testing also high error. In both cases testing error is high and the causes is insufficient model complexity and too few features are excessive, and excessive model complexity, too many features, insufficient training data. Example for underfitting is linear regression for non-linear data, shallow decision tree. Overfitting is it will perform training data good but poor in generalization. So effect on ML models is in underfitting increase model complexity and features reduce regularization. And in overfitting reduce model complexity, use regularization, increases the data. So this is what the underfitting and overfitting. The goal is to build the models that generalizes well to unseen data by finding the right balance. And feature importance and statistical test. To build effective machine learning models, we need to understand which features actually contribute to predictions. This is called feature importance. Feature importance means it measures how much each input, like each feature, helps in making accurate predictions. As we take an example like house prices, features like number of bedrooms and location might be more important than the color of the mailbox, right? And statistical tests are, we use here correlation test, chi-square test, chi-square test and t-test. Correlation test means measures the strength of relation between continuous variables. Chi-square test means used for categorical data to see if distributions are independent. And t-test or ANOVA means used to compare group differences, like whether two teaching methods result in different scores. This is about the feature important and statistical test. Feature important means identify the influential features for predictions. That means identify the important features for making predictions. Statistical test means validate relationships and significance. So here the valid relation that will more important, that will keep here, and together guide feature selection and improve model understanding. This is what about feature important and statistical test. Now underfitting and overfitting, we already see it. Underfitting means correlation versus causation. Underfitting means a mutual relationship or connection between two or more things, like ice cream sales, as we see examples here in both sides. This is what correlation and causation. And finally we move for summary. We covered a lot of ground in this session. Here we quickly recap. Statistics and probability form the foundation of machine learning, helps us understanding data, handle uncertainty and make informed decision. We learned about descriptive statistics, like how data is characterized and how measures like mean, median, mode and variance and all those things. And we learned about probability, including how experiments, sample spaces and event work. We saw how classical and empirical probability along with rules like addition, multiplication help us calculate chances accurately. We dived into distributions like possible, Poisson and normal, learned about z-scores and how standardization helps scale data. We also covered inferential statistics, hypothesis testing, p-values and the bias variance trade-off, all of which are crucial for building effective machine learning tools or models. Finally, we learned how identifying feature importance and using statistical test helps fine-tune models for better results. These concepts are not just academic, they are used in healthcare, finance, transportation, e-commerce and many other areas to make smarter decisions every day. I hope this session has give you clarity and confidence to explore statistics and probability in machine learning further. Thank you for being here. Keep learning and stay curious.